Please, we have Professor Ryan Chakraborty as our keynote speaker for the Society 2024. We welcome Professor Chakraborty for his lecture. So, Ryan Chakraborty is a faculty member in the Department of Computer Science and Engineering at IIT Madras, India, where he directs the Sensing and Networking System Engineering Group. Prior to that, he was a research scientist in the Mobile Communication and Networking Group at NEC Lab, America, Princeton. Owen is broadly interested in the system level design of future intelligence wireless systems and sensing technologies, spanning both algorithm design as well as system prototyping.
The topic, right, as you can see, is the radios are sensors, and radios are basically an integral part of any IoT device that you can see today, right? You won't find an IoT system because the I of IoT comes from the internet, right? And basically that requires you to have a network, and typically it's a wireless network, and that is the radio that I'm talking about, right? It's not the radio where you listen to songs on, right? So it's basically the network interface the IoT devices have. And the interesting thing that is coming up, I mean, this idea was there long back, but this is becoming a reality because of the fabrication technology is becoming more and more advanced, the IoT devices becoming more cheaper. So these radios themselves reflect enough information to capture the dynamics of an environment that could be useful to sense certain things. I'm going to go into details. I'm just trying to explain what I mean by radios as sensors. And the other part that is true for any technology, right, is there are some good things, right? There are like nice applications that you can build around using this concept. Then there are certain challenges with any technology, right, to make it happen, to make it realistic, deployable. That is what I mean by the bad things, right? So it's not really bad, it's kind of challenging to make things happen. So there is some headache that you need to, some effort that you need to put to make things happen, right? So that is what I mean by bad. And the ugly is mostly related to security and privacy issues, right? Because many of these IoT systems are kind of processing sensitive data that you don't want to be leaked out, right? So there is enough chance, right? This radios being used as sensors could be subject to adversarial attacks, right? Which could make things ugly, right? So that is the outline of the talk. There are some applications which are good. You need to make things happen, so it's challenging, right? So that is the thing that requires some effort from the side of the person who is trying to design and develop the system. And there are security and privacy issues, which is basically the ugly part, right? So in a nutshell, this is what I'm going to cover, right? And try to make it a little bit interactive, and there is some tutorial content which is going to be useful for some of you who might be taking it up or looking in this kind of direction in the near future, right? These are upcoming field. So let us look at a basic wireless communication system where you have a transmitter and receiver, right? So that is primarily a data communication that goes on between these two parties, right? And beyond this, we build network layers, and on top of that, you have all the network level primitives, routing, and so on that you do, right? So what we do as a part of this talk is we want to go beyond communication. We don't want to deal with bits and then create packets. What we want to kind of highlight here is we want to understand the signal level primitives that happens underneath these bits being transmitted, right? So any wireless devices, when they communicate, right, follow some kind of an underlying modulation and coding protocol which is reflected as this physical layer signals, right? However you define bits, is a bunch of electromagnetic waves having a certain bandwidth that is just transmitted from the transmitter to the receiver, and it bounces around your environment, which is typically called a wireless channel or the medium, right? So in this room, for example, you can have the ceiling, the floor, the people around us. We all contribute to the reflection and the scattering of the electromagnetic waves, how it is manifested in the receiver side, right? So it's basically shining some light, and the light gets reflected, scattered, and depending on the distribution of obstacles or reflectors, you will find different signatures at different points in the room of the receivers, right? So our kind of the bread and butter of this kind of sensing is really looking into these signatures, okay? So we are not going, as a network engineer is going to do, is going to look at the packets, the binary packets as a primitive and build on top of that. As sensing technologies become more and more like sophisticated, what we try to do is we look at these signals and look more downwards and try to look at the properties of these signals and how do they capture the environment around us, right? That is what I mean by sensing. So if you read, can we harness the versatility of the radio frequency of the electromagnetic waves to sense the dynamics of the physical environment? What does dynamics mean? It could mean a lot of societal applications which could be relevant to this workshop. This could mean fall detection in a camera-free environment. So as you know, in the Western countries, this is a big problem where they do not have people living with them, right? So many old people stay alone, and it is extremely important to detect their fall in case of a stroke or something like that and take immediate action, right? And you cannot really have a deployment of camera all around a building. It's not scalable and also not very privacy preserving, right? There are many places where you don't want a camera. So wireless signals could be used. There are many places where you want to control smart spaces using gestures, right? And probably getting a camera and calibrating all those things, right? Then ambient issues with lights happen, right? Sometimes just hand gesture recognition system might be using for simple gestures. Maybe the signatures of the wireless waves start varying, right? Then you have the traditional wireless sensing applications like robot localization, positioning, tracking, and so on. And not only that, what is quite interesting and that can be achieved by wireless signals is penetrating obstacles that could not be penetrated by visible light, right? So it is possible to know to some extent, right? I'm not really, the way it shows in this picture is really like a science fiction, right? It's not really going to be like this, but there is possibility to know that there are people on the other side of the wall, and this is really, really important for high profile or like high security zones where they want to kind of understand whether there are people around a certain place, or think about applications like you have a large hostage area, right? And you want to scan whether there are victims inside, whether there are terrorists inside, or even if there is a natural calamity, let's the NDRF team goes there, I want to quickly scan through the place under what garbage or what of the concrete or whatever, right? There is life. I want to know as fast as possible and kind of start my rescue operation, right? So lots of applications of such wireless signals that can benefit, right, from the properties of these reflectors and how wireless signals basically behave, right? And of course, if you try to compare it with its nearest cousin, this is going to be the visual sensing pipeline, right? All of this except the through the wall or beyond the wall thing, right, could be done by a camera, and this is being done. Okay, so of course these are all embedded ports, right? There is a lot of bandwidth usage, right? Sometimes you do not want the device to die down because the power requirement is too slow, right? So think of a camera which has continuous streaming of high definition frames to an edge system, and then you have all these fancy deep learning based algorithms, right, that is going to run some detection or some inferencing tasks on those frames, right, which is again a cost bottleneck, as well as like not only the dollar cost but also the bandwidth cost, and that also reflects in energy that is being spent by the edge devices as well as the camera and so on, right? And this is also requires high SNR feeds. What is a high SNR feed? The picture has to be kind of clear. If you do not have enough ambient light, the picture could be blurry or not really clear. So those kind of packages do exist for visual sensing, right? And we are trying to either in some cases replace this pipeline by the wireless sensing pipeline, just about whatever just I told you right now, or we can augment it, right? If we don't want to totally replace it, we can always augment it, right? So it could be an augmentation with some optimization in your mind. It could be that I want to save energy on the MLDL edge, right? I don't want the camera to be on 100% of the time. Only when I think that the camera should be on, you should turn it on based on some co-processing or co-sensing that is going on, which could well be the wireless sensing, right? So this is typically where I want to kind of pitch in, right? And our kind of contributions or the kind of things that we are looking at from our group. So there are cost performance constraints, right? When you do the visual sensing pipeline, and in some cases it could be an overkill, right? So sometimes we use the camera to detect whether a person entered the room, right? I'm not really looking into whether like trying to detect the gender of the person or not trying to really recognize the person, right? So you do not need a sophisticated face recognition algorithm to know that there has been an intrusion in the room, right? But that is sometimes the case, right? You have a camera and the camera typically sends out the frames and those frames are processed, and it definitely is an overkill, right? So we are trying to look into n number of sensors that could do the job for you in a much more compact or cheap and energy efficient way. And one such example is wireless that is more versatile, as I told you, right? So inertial sensors are there, acoustics, there are many sensing modalities, and each such sensing modality is going to have some kind of a limitation, right? Whereas RF is something that is ambient because of the deployment of access points or any other kind of wireless technology that you are seeing around us, right? Bluetooth, they are kind of more versatile in the sense that they have a like lot of power to capture much information about your surroundings, right? That basically follows the laws of physics because it's all Maxwell's laws that we are kind of depending on, right? So this is kind of the talk outline. So we have some application enablers. So whoever is interested in kind of taking this and exploring this primitive sensing technology in your work, there's a lot of opportunity. There's a lot of papers that has been published in trying to come up with innovative applications where wireless sensing could be used. So it's an application enabler. That's the good part, right? To quote whatever I named in the title of the talk. Then there is this part 2. As I told you that there are computational challenges, right? I will do wireless sensing fine, but if the amount of computation that I need is more or equal to or comparable to the visual pipeline, then there is not much of a point in doing this, right? Other than just another modality, right? I need some point to make it attractive to a system level designer, right? So we have to see what kind of communication or computation challenges exist in order to like marry wireless sensing to an IoT device, right? And then is there any way of doing adversarial exploitation of such sensing techniques? Because fundamentally, this is wireless signal is a broadcast medium, right? It's not that I own this part of the medium and you are not, right? There is no territory, right? As long as the signal propagates, anybody in the medium should be able to tap into the medium and do whatever he or she wants to do with the captured signal, right? What if the intrusion example that I have given you right now is used for adversarial purposes? Maybe I do not want to leak the privacy or leak the, let's say, the occupancy of this room, right? How many people are sitting here is, let's say, a private information, and I don't want this to be captured, and I have made sure I don't have cameras in this room that will capture this information. But maybe I have an adversarial node that has been trained to look at the wireless signal and infer at least how many people are there. I'm not really saying people counting that there are 16 people or 17 people, but let's say more people, less people and all. This could be confidential information for some, you can come up with an application for that. But this is what I mean by adversarial exploitation of this kind of modality, because there is no hard and fast rule that I can really put on a wireless medium, right? I cannot construct a wall around me and make sure that the signals do not penetrate there. That is indeed the case in high profile places like White House and all, where they really do not want any wireless signal to come out of, let's say, the White House or Parliament or whatever, right? So, looking at the, now, you can interrupt me and ask me questions, that is kind of an introduction to what I will be talking about. So, these are the 3 things that are kind of interesting for pursuing research in this area, right? So I'll go to a little bit of more technical details and try to show you what kind of metrics are actually used in such things, right? So if you are aware of wireless LAN, right? So 802.11 stands for the WLAN IEEE standard, right? You have 802.11a, b, g, n. Now it is AC, AX, and so on. So this is a series of the IEEE standard, and this has become the sensing has become so predominant, right? There is a task force that is dedicated for using the current Wi-Fi chipsets, right, to be doubly used as sensors also. And this is something that is proposed to be kind of the first draft is proposed to be completed by 2024, right? And it's called 802.11pf. SENS is the name of the task force for wireless sensing. So as you can see that although the ideas existed, right, from the radar literature long back, but this is something that is going to be really incorporated in the standards, which actually mean that commercial devices or commercial entities are interested in leveraging this kind of information in executing some of their tasks, right? Like this is Cisco or Qualcomm or Broadcom, right? They are the ones who are going to integrate this kind of functionality, maybe expose them as APIs, and you as a Wi-Fi driver, software engineer or system software engineer would be able to expose this information through the application developers, right? So one quick example could be if most of the people are concentrated on one corner, I don't want to broadcast the power of my Wi-Fi on the omnidirectionally, right? And now this is going to enable that most of my Wi-Fi users are only on that corner, and I want to beamforming that corner, right? So this kind of things are going to be enabled naturally in Wi-Fi, right? So we have the mechanism to do beamforming, but you need to know where people are.
But now that is a part of the current version of the MIMO technology that supports.
So MIMO is the technology that enables this, right? But for still you need to do a beam search, or you need to know where people are. Sensing is going to do that, right? So there are like a few simple metric. If you are in the wireless domain, you probably know that. So one is the wireless path loss or the received signal strength that is being received. It's very simple. You have a transmission device that transmits a power of PTX, right? And whatever you receive on the receiver device is some watts, right? This is PRX, and the difference in between them is basically the amount of power that is lost in the medium, right? So if you have a concrete wall, the loss will be more, right? If you have like free space, the loss will be less. So it depends on the distance, and it attenuates along the distance, right? So you have all practical experience with this. If you go more and more farther and farther from the access point, your power keeps on diminishing, and at a certain point of time, it's kind of lower than your noise floor, so you are not able to decode the packets anymore. Okay, so you have a equation, like analytical equation to express this. And there are many analytical models to express this. This is one simple way, it's typically called the log normal model. As you can see, there are two interesting or dominant factors. One is D, the other one is this gamma. So D refers to the distance in between the transmitter and the receiver. Farther the D, longer the D is, more is the path loss. And gamma is basically something called a path loss exponent, which depends on the material properties of the medium, right? If it is going through metal, of course it cannot penetrate metal. If it is going through wood or maybe some other kind of thing, the loss is going to be a function of the permittivity of the medium, which basically you know from basic physics, right? So it depends on the distance and the obstacles. Okay, obstacles could be either you penetrate the obstacle or you also the obstacle reflect, right? So it's kind of a function of that, but this metric is a scalar, right? You just basically have a path loss value, and that's all. Okay, so I have a few pictures that I have done with the volunteers, like our students of our lab, right? This is Amartya sitting here. So we have a transmitter, we have a receiver, human attenuator, right? So if you pass a signal like this, right, the RF propagation is going to be affected, and you can start looking at these values, right? And that can, without Amartya carrying any device, right, I would be still figuring out that there is a person who is there in the link, right? Now you can extrapolate this idea and try out this simple concept. Let's say you want to wake up a camera when a tiger passes the link and you want to count that timestamp that tiger has come, right? We don't have to really have the camera 100% of the time on, it could trigger, right? There are other sensors to do that. I'm not saying that I have to do this, but I'm just trying to say that this could be used for those purposes. Then this is like the raw received signal strength that you have because of his presence. And again, you can extrapolate this idea to something called, let's say, crowd sensing, where I have 1 person, 2 persons, 3 persons, up to 4 persons, and we can very easily see that the loss is proportional to the amount of obstacles or the amount of material that we put in the link, right? This is an empirical evidence, and it pretty much follows the log normal model that we have verified, right? But just with this data, you can get an intuition that, okay, this is enough to maybe build a classifier, a very crude classifier.
So you are using normal receiver?
Yeah, it's just a RSSI receiver, right? Yeah, please feel free to ask or clarify. So this is like a wireless receiver that just logs your RSSI. It could be a smartphone even, right? And this kind of data, if you really try to look at the distribution, you can see that a very well separable likelihood distributions, right? Even something as simple as a straight line separator like an SVM or even a naive based kind of an algorithm is going to, I mean, you tried it out, is going to function very well, right?
In this case, transmitter is the node and receiver is the access point, or?
Anything is
Okay.
fine, right? Because this is kind of bidirectional link, right? So it could be basically two wireless nodes that exchange communicate.
So you are getting data when you are transmitting the information?
For every packet I get a sample, right? So this is kind of a very orchestrated setup, right? As you can see that, oh, there I asked these 4 students to stand so that the things look good and I put those plots, right? So, but now we need to kind of see that this is not something which is very practical, right? Nobody will stand still like that, and right, this is okay for like a proof of concept or trying to understand that whatever we have formulated works, right? Yes.
Here the obstacles are in the direction of the flow of signals. So
Yeah, I mean this direction of the, I mean it's called flux, right? Electromagnetic
the
flux.
position will be different, then the signal strength, relative signal strength will be different.
Will slightly change, but still if you see the factor gamma, right, which is basically a function of the obstacles around you, you will still see this signature. Right? You have more people, you have more mass in the path, you have more loss.
So can we, we can confirm that whether the obstacles are in the direction of the where the signal is transmitting and whether the obstacles are side to that?
Not really. I mean, what you are saying is like line of sight, non-line of sight thing, right? But I mean, still it does not have to be the case. If you have more reflectors, the signatures are definitely going to change, right? But what I said is this is a little bit too simplistic.
Yes.
If you add more dynamics to the environment, that is what I'll show, things start failing, right? So this is an example of same 4 people walking around. So when they start walking around, all your nice likelihood distributions collapse, right? And we are hopeless here. That the thing that gave us promise doesn't work, right? So this kind of situation is something that is going to come up more often.
In this case, like the sensor, like the transmitter has to continuously send the.
Yeah, it's kind of, see,
right?
any access point keeps on sending something called beacons, right, or hello packets. So you anyway keep on getting those packets on the receiver, right? It's not really data, it's something called keep alive.
So it has to be periodically sent.
It is sent as a part of IEEE protocol, like 802.11 protocols, right? It's called beacons. Okay. So to capture this kind of things, right, we need to have something which is robust enough, right, to kind of take care of these details. Okay. So remind me of the time.
It's okay.
Yeah.
This was it.
So typically this is called wireless multipath. Okay. And wireless multipath is something that captures the properties of the reflectors around an environment. Okay. So what we earlier had was a scalar, and this scalar is basically a path loss. You get a single number. What was the total attenuation? Right? That does not capture much details about how it was attenuated. It was attenuated for a longer distance, or it was attenuated even in a shorter distance but more obstacles. Right? Or you have too many reflectors around you and it kind of like destructively interfered and all, right? So those are many reasons why your signal could be very poor. Okay. So we want to look at a new
Another
primitive.
question. That signal may be impact on weather condition also,
Yes.
na? Humidity,
Yeah,
temperature, inside.
weather conditions, but typically we are looking into indoors. Indoor, I mean, it would definitely depend on the permeability of the medium, but I think that extent is very less. Okay. So what we have as the line of, what we call the line of sight path, is the direct path in between the transmitter and the receiver. And you will also have, in a practical environment, many non-line of sight paths. Okay. Because of the presence of these reflectors, it is going to follow, I mean, you all know light, right? Light gets scattered around when it gets, it's not just a laser beam that only point A to point B, but there are other places it kind of reflects around. So, this is nicely captured by a wireless receiver. Okay, and the crux of this phenomenon, this is kind of very important, is the straight line path is the shortest possible path in between 2 points, right? If you have any other path, that path is technically longer, right? It cannot be shorter than that, which means that those paths are going to take more time, right, to reach the receiver. So you can think of this as like echoes of the same signal. Echoes arrive at the receiver at different points of time, and if you know the time when which the echo arrived, you can start off kind of thinking of a locus of where the reflector is, right? So what you really get is something like this, right? The x-axis is time, and the y-axis is called amplitude here, right? So these are the infinite number of reflections, technically infinite number, but you can only capture a finite number based on the time resolution. So this is like the T0, which is the direct line, like straight line path, right? Your signal cannot travel more than the speed of light, right? So T0 is the minimum time that is, let's say, required, and this is something that any wireless receiver gets. Without that, you cannot really decouple the echoes from the real signal. And this is the heart of any wireless sensing technique primitive. This is the data on which most of the wireless sensing takes place. Okay. So if you look at the other tabs, let's say the blue ones, tau 3 and tau 6, those show strong reflections, which basically means that there are paths that cover a distance of tau 3 into c. C is the speed of light. Time into velocity gives you distance, right? So tau 6 into c is another path where the signal has traveled to. Okay, and this is our time domain signal, which is basically called the channel impulse response. Any packet that is being sent from a transmitter to a receiver manifests itself in this way. Any packet, like basically you don't, I'm talking, right? You are hearing the straight line path, but your brain is also cancelling the echoes that you are actually receiving from these walls. The brain is very good in doing that, right? This is exactly what the wireless receiver does. Okay, so if you take a Fourier transform of this impulse response, what you get is called a frequency response, right? And this vector, which is typically a complex value vector, because it will have this I and Q samples. I'm not going into the details, but this is what is something that is available on most of the Wi-Fi chipsets. So if you buy a Wi-Fi chipset from the market today, this is going to expose that yellow vector, right? And this yellow vector is something that captures a lot of information of the dynamics of an environment. Okay, and this vector is available for every packet that is being received. Okay, so I transmit a packet, I get this yellow feedback, right? Which is typically called channel state information. You transmit another packet, I receive this information, right? And in between, let's say you guys are moving, I could start kind of understanding the dynamics of this room, right? Maybe there is a lot of movement on this part of the room, less movement on this part of the room, right? So this kind of things are kind of stacked together in time domains. So this is what is called the CFR, right? And you get many of this part packet, right? For every packet that you send, and what you create is basically called a spectrogram. right? Here this x-axis is this yellow blocks, and you stack them for every packet that is being sent, and what you get is this time frequency matrix that is basically the sensing data, right? So now you understand that how you have a wireless radio and what is the sensing data primitive that you get, right? If you have a temperature sensor, maybe it's some kind of a resistance, right, that is calibrated with temperature. Similarly, if you have a wireless sensor, this is the sensing primitive, and now you can do a number of your ML algorithms that it will be applied to this and try to do some inferencing and all, right? So this is the actual communication primitive that is available, right? So now I gave you this example where more people, like 4 people are moving around, and we saw that if you just use a path loss scalar value, that was not efficient enough to capture these dynamics of the environment. But if you simply replace this with a more meaningful information that really captures 4 bodies, human bodies moving around versus 1 human body moving around, that clearly shows a distinction, right? If you see these 4 pictures, we have trained and we have enough evidences not only from our experiments but also experiments that has been done by other researchers, and it's extremely established fact that this could be used as a very good classifier to understand the dynamics of the environment to some extent. I will not probably understand like the movement of your fingers, right? But in a general sense, right, in a macroscopic scale, because of the wavelength, because it is dependent on the wavelength of the signal that you are using, this is going to give you good enough information about the macroscopic dynamics of an environment, which is really nice, right? Because this is something that you really get for free. You don't have any extra sensor or anything at all, right? Any house that has a Wi-Fi transmitter illuminates the room, right, with Wi-Fi signals. And any receiver that receives this data, you have to receive this data, otherwise you cannot decode the packet, right? They have access to the data, can have their own inferencing engine to do whatever he or she wants to do, right? Whatever application they want to enable, right? So this is one example, and then we did a lot of fun experiments. I can just want to make the talk enjoyable, so I have a lot of fun experiments that our students have done. So we try to do it on our bus, right? We are all, how many of you boarded the campus bus, right? So the bus, if you have gone, we are trying to, we are kind of interested in understanding the occupancy of the bus, right? So we had a transmitter in the front of the bus, we put a receiver in the back, and then we tried to understand how the dynamics of the bus changes and whether something is just a fun, right, with no big intention, right? We just try to understand how it behaves. Can we mine something interesting from it, right? So it turns, I'll give you snapshots of our experiences. Let's say when this child is coming out, right? You can start seeing the fluctuations flourishes. Right now it's kind of settled down. So, I mean, this gives you ample opportunities to know that without using a camera, which could be you need a lot of clearances to put a camera on the bus, and why do you want to use it, and then to store the data. This is much easier way to even know that the bus has stopped, people are coming, right? Using wireless sensing. And
So what is the error rate here?
We did a few constant trials, and we found out with RSSI it could be within 80% to 70 to 80%, right? Because of the bus movements itself, there is some kind of a, yeah. So now I'll.
Bus movements and the obstacles, the lot of
But those are constant, right? So you cannot just train it on this data, but you need to kind of have some noise filtering, right, to take out the static part of the bus. So we also tried out something like this, right? We also collected the spectrogram, right? So x-axis is time. So for every packet that is being sent, I plot the CSI in the y-axis, right? So this is your the yellow blocks that I've shown. That is just horizontal, vertically put, right? So though the amplitudes are vertically put, right? So this was a pleasant enough surprise that you can actually find out the number of bus stoppages from this data, right? If you just do a simple clustering of this data, you can see there are red blocks and there are blue blocks. And this correlated very, very well to the bus stops that we had on campus, right? So with zero amount of camera or zero, very, very minimal processing, that gives a very nice idea of how long the bus stopped, timestamps of that, right? And it is fair enough to ask for a Wi-Fi access point on the bus, right? This is typically when we are even proposing those kind of things for the students to access on the bus, right? So these are all interesting byproducts, like engineering byproducts that we have, right? This is nothing like very new in terms of physics. The physics has been there for a long period of time, right? This is something that we are trying to enable it in terms of an embedded system IoT application. Okay. So another nice thing that I can show you is here, right? We are trying to make cameras more efficient by kind of reducing the sleep cycles, right? Or kind of increasing the sleep cycles. When there is nothing, I don't want the camera to capture information, right? So if you see that this person is around, it's a very clear signature, and we can also figure out is a person on a bus or a cycle or a pedestrian, right? And accordingly I can increase the resolution, decrease the resolution, save a lot of power, and basically go towards battery operated cameras. It's an extremely important problem, right? How can you make cameras disconnected from the wired grid, right? Both in terms of power as well in terms of networks, right? Immense application of during elections, right? We don't want people to go and cut down the wires to deactivate the cameras, right? There's a lot of application of having battery powered cameras, ad hoc, deployed ad hoc, right? So this is another thing. So I'll talk a little bit about
also the DR movements in the roads.
Huh?
So instead
we have to try it out, because if you deers may start eating it up. So and the deers do attack those camera systems.
So I'm not telling that using the Wi-Fi signals, maybe
Yeah.
you can measure that deers are nearby, and maybe
Yeah, it could be done.
Sometimes in the rainy season camera will not work, so maybe it will penetrate somehow.
Yes, those things
will
can
give
be
more
done.
information.
Yes, and I think there is enough, we have enough expertise to understand that whether it is a human being or a deer,
Yes, yes.
right? Those kind of things can be done. So now I'll try to talk about the relatively challenging things, right? And there's like open research questions that exist here, right? Trying to make this wireless sensing edge friendly. So today, this is a typical setup where you have a camera, and through the wireless network or an optical network, you send it to the edge device, which is typically a matter of a few Mbps that is being constantly streamed at high definition, right? The network providers, the edge providers do not complain because they make money from it, right? But this is some real loss for the operators of the IoT devices, right? Because I do not want to stream data if there is no necessity of streaming the data. And also I want to kind of preserve the energy as much as possible to make it potentially battery operated, right? So we can just cut down like on this Mbps to like a few order of magnitudes, right? Maybe kbps. So if you just replace the same system, right, in this kind of a scenario, right, I'll just replace it by an RF modality, which could be augmented with the camera. I'm not saying that totally replace the camera. Of course, camera has its own good things that can never be replaced, right? But if I am just interested in something which is very broad and I do not want highly granular details, I can come down to kilobits per second, which is very energy friendly. And when I come down to the lower bandwidth technologies, I can use a lot of low power technologies that actually supports low data rates. Okay, like LoRa and so on, that gives you long range, and low data rate is okay, right? I'm already using low data rate. Cannot be done if I'm doing camera. It requires LTE or it requires an optical connectivity.
Another point is if when someone is not there, if I reduce the rates,
Yes.
then the lifetime of the camera will be increased.
Yes, that is another thing, right? So if there are nobody, right, the resolution we can diminish.
Yes, yes.
So I'll put a few ideas, and if you tend to work in a similar domain, you can pick it up, right? So these are the kind of experiments that we have done for human activity recognition. We could figure out standing versus walking versus jumping versus like a null hypothesis, right? Like it's empty, and it's very straightforward. ML classifiers is probably not working, right? But very energy friendly. Typically, these things has been done using computer vision, and they'll create. Those are extremely hungry in terms of GPU resources. Here there is no question of any GPU or nothing, right? We are doing everything in a microcontroller.
Another point is the assistive living, na? So bathroom, you cannot place camera.
Cameras and all.
So maybe if I place this Wi-Fi kind
Yes.
of, I don't know what is the accuracy of, because there is a very less accuracy
Yes.
in down, sometimes down.
So falling down actually
Yes,
creates a
yes.
very distinct
Yes.
signature. So that is something that, I mean, there are even papers on those things, right? So here the idea is to make it more edge friendly so that we kind of cut down on the amount of data, right? Sorry? Yes.
So these activity recognition, these were done for one person or multiple people?
No, this was done for multiple persons. Mix, yeah, not one person.
Mixed.
Not only multiple person, but multiple locations.
So we can get the signatures that who is jumping, who is walking at the same time.
I mean, same time in the sense I can infer whether he is jumping or he is one of the 4 classes. Yes.
Like for multiple people in a room, we can do.
No, that will be, yeah, it's a very interesting question, right? So you have a mix of these signals, you have to make something more intelligent, right? You need to do some kind of like a mixture model, separation kind of thing, right? This is not something that I'm talking about, but that is a potentially nice problem to work on.
Sir, just my understanding says that, so whatever you are doing here, it is only a device or only a signal which is moving in a one direction, or that is not a orthogonal direction. If you put some sensor which is orthogonal, then you can
It does not have to be inside the link, right? Suppose there is a transmitter on that corner and the receiver on the other corner, right? It will still, I will still reflect.
No, means if it is orthogonal, there are two devices or two signals which is orthogonal in itself, and if you sense the different signals, then maybe you can infer something more.
I do not understand the question properly. So orthogonal means in terms of location.
He's saying that one over the other.
One over here,
roof
one
and
signal is in
ceiling.
this way, another signal is in this way.
Okay, so you need like you are now having more data, right? More sensors.
Yeah.
The more sensors will of course improve the.
Then you can have some more classification.
True. I mean that is yeah. If you put more sensors, it will be better, right? But given that you have to follow a MAC protocol, if you have 2 sensors, these are radio sensors, right? They cannot talk simultaneously. So you'll end up having the same data rate. But what you are saying, it will give you more geometrical diversity.
Geometrical diversity.
Yes, that will be there. Right. So a few solutions we are trying to
But
look at. Yes.
two sensor can talk now. If I place some kind of controller with them, then maybe somewhere it is possible.
So we are actually talking at a packet level, right? So you need to make sure that this is fast enough, right? Within the every packet we actually
nanosecond.
After getting the two signals separately, then you can do some processing.
Yes,
over time.
true. That is something that can be done, like so distributed sensors. So here one of the things that we are kind of exploring is that like how do you cut down on the precision of these IQ values? There is a complex value, if you remember, that I talked about. You do not even need 8 bits, right? So I can actually even cut it down to 1 bit and still have some accuracy, right? So this is going to reduce the size of your data. So these are some examples where I quantize the CSI spectrogram to even 1 bit, right? And there is some kind of a pattern that will still come up, which is very specific to a given kind of an environment, right? So this is basically a quantized spectrogram. We are using 8 bits, which is the original resolution of the IQ values. Now I can go to 4 bits, 3 bits, 2 bits, and so on. And you can also compare that from 8 bits to 1 bit, we actually did not lose a lot, right? So what I would say, this is called the diminishing returns. I do not really need 8 bits. Even if I use 7 bits or 6 bits, I almost do not lose any accuracy. So these are like top level pointers, like this kind of superficially presented. But these are the nice research questions that you can delve deeper into, right? For a given kind of an HAR system, how can I optimize the bandwidth to make the system very network friendly without giving up on accuracy, right? Another interesting thing that is kind of worth looking at is the low rank nature of the spectrograms, right? These are not really human faces or like a picture of a dog or something that is a very high rank information, right? This information inherent is very, very low rank. And given that you are trying to build a certain kind of application, you do not have to really send out all the data. You can compress it to a high extent. What rank you are going to compress it on depends on the application, right? So you can do like a SVD, right, and truncate, like I think all of you are aware of this linear algebra, it is like singular value decomposition, right? So you can truncate, right, some of the singular values, right, and have a low rank representation of the spectrogram. And we can show you some examples where even with a very, very low rank, I am still able to meet up the expectations of the classifier model, right? And that results in saving a lot of data, right? So, for example, this is a rank 10 spectrogram representation, which will probably have some very high accuracy value. But you can actually go up to even rank 1, which is not really bad, right? And suppose your application is simply trying to detect that whether a person entered this room or not, you might be overdoing if you are actually using the entire CSI spectrogram and not really compressing it. So there are many, many such avenues where network friendly behavior from the IoT could be exploited, right, and explode, right? So the rank of the spectrograms is something that could be exploited to make this sensing more network friendly, right? So even with a very low rank approximated spectrogram, this is something that we have already done internally, and we found evidence that it does not affect the classifier models, modulo the kind of models that you are looking at, right? What is the how much information that you need in the models is really important here, because you lose information here, right? So so these are some of the nice problems that could be kind of explored, right? How to balance the computation and communication bottlenecks, right? The IoT devices are going to have the CSI spectrograms. How much you want to send to the edge? If it's a rank 1, right, it's really happy. You don't have to send too much information to the edge, right, because of the compressive nature, right, of the spectrograms. So I'll just conclude with the final point which I kind of raised in the very beginning, which is basically the adversarial attacks, right? So what is an adversarial attack that you can potentially do in this kind of systems? You have a transmitter and you have a legitimate communication and sensing device. Okay. So, but this medium is accessible to all anybody who is there in the physical vicinity. If you are in physical vicinity of the medium, you can get access to the signal, right? And anybody can, right? Which could be a adversarial sensor, right? Which could be doing something which is not intended. Okay. So it has access to the medium and has these trained inference models. And those trained inference models is something this adversary is going to use to detect what it wants to, and this is typically a private information that you don't want the adversary to detect. Okay, but you can't stop it. So this could be anything, right? It could be actually it could be just ambush behind the walls, and it has a lot of privacy security vulnerabilities, right? Where the intruder could do, or the intruder could even be a robot, right? Which is just ambush, and whenever it thinks that it has the information it needs, it can do something that is not anticipated, right? It can also result to privacy leaks. So one example is even your smart TV would be able to now gauge the audience sitting in front, right? So today, if you are opening Netflix knows that somebody is watching, right? But these OTTs want more information, and this is, believe it or not, the OEMs, the LGs and the Samsungs are extremely interested about putting this kind of technology on the TV, right? Interested means that in the effect that we have a project which is in the similar lines. They already have a microphone on the remote control, right? Which is a no-no for the European countries, right? So now they go for a wireless chipset on the TV, which is already required because it is a smart TV, right? They start exposing this kind of information to the Netflix and the YouTubes, right? That gives you a lot of information about the audience, like the audience, like maybe children. They can start detecting things like whether they are moving around, they are sitting on a couch, there are small children watching them, and they have like lot of good things that could be enabled, right? So all this parental control, children watching the TV from a very short distance, this kind of things could be started to be like rolled out in the smart TVs, right? So this could be something that you don't like, or maybe the LGs and the Samsungs like it, right? So that's a different discussion, but privacy leaks is another thing that could potentially be stopped, and you can have an intelligent access point which could stop this kind of privacy leaks, right? And this is the last slide. So one of the solution is that you can potentially, there is technology to very selectively add randomization to the signal at the access point without disturbing the data. Please understand, this is not the data that we are kind of working on. This is the echoes of the data, right? So if I shout in front of a mountain, right, there are 10 echoes that could be coming back. The content what I shouted, right, that doesn't change. It's just that there are multiple echoes depending on how many mountains are there, right? So that is a reflection level signal which could be potentially perturbed from an access point as a security measure, right? But of course, there are pros and cons, right? So if you have the original signal like that and there's a highly perturbed version, you might falsely think that there are too many reflectors, and based on that you might change your transmission patterns. So you might end up in actually a lot of data rate loss, right? If I hear there are too many echoes, I will try to think that, okay, there are too many reflectors, I'll shout more loudly, right? Which could be really not required because those echoes were false. It was injected by the access point itself. So there are very, very nice problems where these adversarial attacks could be kind of treated, right? How do you make the systems robust and resilient to such kind of attacks, right? So we tried out various kind of techniques called LIME and all, right? So that specifically looks into what kind of perturbation could be done on a given feature, like feature vector or a data, to make it just misclassified, right? And you have to do it very intelligently. And all these things are going to be running on the next generation access point, which is going to be secure in terms of sensing. And so, so basically this could heavily impact the data communication, right? You cannot just go and add random noise, right? This will heavily impact the data communication. So you need an intelligent and natural perturbation technique, right? Or a set of techniques that are going to be robust enough to not break down the communication system, but efficient enough to make the adversarial attacks get spoiled, right? So it's kind of a trade-off that is there, and this is an active research area that many people who work on wireless sensing looks into these kind of problems, right? So example is it's FGSM, it's a classical technique to convert, like make a AI model fool such that the dog is classified as a cat, right? You are all aware of this one pixel attack. So you can just change one pixel in an image and your classifier thinks this is not a dog, it's a cat, right? For a human being, we are very robust. We understand that this is a cat, right? So there are techniques like this that could be, that we can leverage on, and depending on the computational complexity that is required, we can actually make access points more intelligent, right? And this is the final thing, right? Can we make the communication systems resilient to adversarial sensing attacks, right? The first slide that I had in this talk was that 802.11 BF is a new standard that is coming up, right? And it's almost there to be deployed on commercial chips, right? Can I try to augment those standards using appropriate countermeasures that will make the adversarial sensing kind of not very effective, right? We are making the communication systems robust enough to stop adversarial sensing, not at the cost of communication, without having a minimal impact on the communication. So this is pretty much the ugly part of it, right? Which is basically something that we need to work on, try to make the standards more reliable so that these ugly things don't happen, right? Nobody can adversarially exploit this wireless communication medium, because anybody who has physical access to the medium could be doing bad things, right? Or things that are not anticipated, right? So I'll conclude the talk, right? The customary picture that we have from IIT, right? These are the two to get a little bit more.
Excellent presentation. Now we need video.